Where we're going to be today is primarily with radioactive decay. Let's talk about what we talked about before. Just in a review, we've got our three fundamental particles that we're focusing on are the proton, and the charge of the proton is, and it's located inside the nucleus. Exactly. What does proton determine?
The
element, the atomic number. It is the atomic number. The number of protons equals the atomic number, which equals the element that we're talking about. So where is the neutron?
In the nucleus.
In the nucleus, and its charge is?
Positive and negative.
Positive and negative. Very good. Making it neutral, and I'm going to kind of throw a monkey wrench into that too. But at any rate, we're going to think of it as being positive and negative, just for simplicity's sake. And those charges cancel each other out, and therefore it's neutral. And then that's also inside the nucleus. What does it add? Weight, mass. It's just mass, right? So more on that here in a bit. And the electron exists
In the shell.
in the shell, right? And a lot about the shells there. So we'll put that on hold for just a second. Where is most of the mass of the atom?
In the nucleus.
In the nucleus. What is most of the area of the atom? It's empty. It's empty space, right? So most of the mass. Okay. So the electrons. So a few things about the electrons. How do we number the shells in electrons? What's the innermost shell?
2n².
Okay, that's how many electrons you can have in a shell. But what's the innermost shell? What do we call it?
K-shell.
K-shell, right? So K-shell, and then it's alphabetical after that. So since you already touched on it, how can we calculate how many electrons can be in any given shell? 2n², right? So how many electrons should be in the outer shell? 8. No more than 8. Remember to read the question, differentiate between the question. Remember that all the above can't be a selection if one of the answers is wrong, just like true false, right? So outer shell is always going to be 8, but theoretically you can calculate how many can be in any shell with 2n². So we measure the binding energy in keV, very good, which is similar to, or actually identical in its power to kVp, exactly. So the binding energy is always going to be closer to, I just gave that away, always going to be closer to the nucleus. So the closer you get to the nucleus, the higher the binding energy is, kind of like gravitational pull. Is also like gravitational pull in that the bigger the nucleus, or I guess a better way to say it is a more dense populated nucleus, the higher the binding energy as well, right? And how that affects us is both in our characteristic and our Brem's X-rays. If the electron gets close to the nucleus, it's got a high atomic number, high atomic mass, then we create a high energy Brem's X-ray photon. And then those binding energies, if we can knock out that inner shell electron, then we can create a X-ray photon equivalent to that binding energy, which is 69.5. So okay, so then we talked about centripetal and centrifugal force. We said centripetal force was kind of like gravity. It's what keeps the electron from flying away. Right? And then centrifugal force is what keeps it's basically the speed of the electron. We use the planets as an example. I forget what a year on Mercury is, but it's like, I don't know, something ridiculously short, like 28 days. Anybody know? 28 days? Yeah, so it's just screaming around the sun. It takes us a year, right? So centrifugal force is basically, in that analogy, the speed of the planet. It's what keeps the electron from falling into the nucleus. So we talked about atomic mass. We talked about atomic mass number. Atomic mass is the actual mass. Atomic mass number is a rounded version of that. And we talked about the rest of atomic nomenclature. An isotope, we're going to talk about isotopes here in a bit, is a atom that has the same number of protons. Protons are positive, right? And they're inside the nucleus of the atom. And they determine the element, right? So it has the same atomic number, so it's the same element. It just has a different mass, atomic mass, which means that it's got a different number of neutrons, right? So, just to preface radioactive decay, a nucleus can get so heavy, so to speak, that it becomes unstable. So we'll talk about that here in just a minute. So then we talked about, and those are isotopes. Isotones, they don't really have much of a place here in what we're doing, but the same number of neutrons, oop-de-doo, right? And different number of protons, so it's different elements. So isotone, isobar has the same mass, different number of protons, so also a different element. And then an isomer is just same, everything's the same. So fundamentally the same thing. So we talked about combining of atoms to create molecules. So we had two different ways. I had to find myself in my notes here. You've seen my writing, right? I can't read it either. So combining atoms, we've got two different things. We have ionic, and that is where one atom gives up an electron, another atom takes it. They both become ionic because they both have a charge now. One becomes positive, one becomes negative. Opposites attract, and therefore they come together to create an ionic bond. And then we've got covalent bonding, which is also sharing of electrons, but the goal here is to get 8 in the outer shell, and we drew, H2O on the board as a demonstration of that. And in that, both, even though they're all three atoms were sharing the same electrons, it brought 8 into each outer shell. So hydrogen had 8 in each one of the hydrogen atoms, and the oxygen had 8 as well. So we talked about a lot, right? So any questions on all that? If you've had a chance to look over the review, any questions on the review?
What is the goal of ionic bonding?
The goal of ionic bonding is to become neutral, share electrons, become neutral. So in both cases they share electrons. The goal is different. With ionic bonding is to become neutral. With covalent bonding is to get that 8 in the outer shell. Okay, any other questions? All right, so then we need to get into radioactivity. So again, when we have an atom that becomes too heavy, so to speak, to support itself, then we have what we refer to as a radioactive isotope. So it's an isotope, it's an atom of a specific type, but the nucleus is too heavy to support itself. So it seeks to become stable. It's unstable, so it seeks to become stable through radioactive decay. That's what we really refer to as radioactivity. We've got radiation, we've got radioactivity. Not all radiation is due to radioactivity, all right? But in this case it is. So we have two different ways that a radioisotope can become more stable. And what it has to do really is with either protons and neutrons, or neutrons themselves. So we have two different ways. We have alpha decay and we have beta. Okay, so with alpha decay, what you've got is you've got this great big fat nucleus that is too heavy to support itself, and it's got to get rid of a lot of stuff. So uranium, for example. Uranium is a great big atom, right? It's got a lot of protons, it's got a lot of neutrons. Let's say uranium-238 and 235. I wrote down in my notes, uranium-238 and 235. So what you've got are atoms with great big nuclei, and they've got to get rid of some of that, okay? So what alpha decay is going to do is it's going to take a chunk of that nucleus and it's going to kick it out, okay? So what you're going to have with alpha decay is 2 protons and 2 neutrons being ejected from the nucleus of the atom. Okay, so what atom has 2 protons?
Helium.
Helium. So basically what we're doing is we're going to eject a helium nucleus from the nucleus of the atom. So let's let's go with something hypothetical and something simple. If, let's say, before this happens, we have an atom that has 100 protons, and it's got 100 neutrons in it. Okay, so it's got 100 and 100. So if we eject 2 protons, 2 neutrons from it, then first off, my atomic number is 100, right? So that's our atomic number because it's the number of protons. Our atomic mass, though, is 200. Right, so if I kick these out, then what's the atomic number of that? 2. What's the atomic mass of all that? 4. Right, so what happens to my atom at that point? It drops now from 100 and 100 to 98 and 98. And so what I've got is 196. So in that, what have I changed?
The element.
The element. The element changed. Now we've got a totally different element. It's a different animal altogether, right? But the elemental mass dropped quite a bit as well. Okay? Everybody good with that? Alpha decay, we get a helium nucleus. That's two protons, 2 electrons kicked out of the nucleus. And, you know, it's going to go grab a couple of electrons, and it's going to be helium. Okay? So what happened there is our atomic number decreased. Okay? Now with beta decay, what you get is the ejection of 1 electron from the nucleus of the atom. Okay, so where are negative charges in the nucleus?
The neutron.
In a neutron, right. So we've got 1 proton, 1 electron to create a neutron. Give it all over neutral charge. So if we kick this electron out, then what am I left with there? I've got now 99 protons and 97 neutrons. What's my atomic mass? It remained the same, right? But my atomic number then went up, right? So with alpha decay, atomic number decreases by 2. With beta emission, atomic number increases with each one of those interactions, increases by 1. Okay? So in the case of, and the reason I wrote these down, uranium 238 and 235, uranium 238 and 235 undergo both of these. Over time, they emit both of them. So what you're going to learn next semester in radiobiology is that alpha particles are great big, comparatively speaking. They're great big, they're slow moving. They have to have something to make them go, essentially. Okay, so they're, you know, if we had, I don't know, a chunk of uranium, I don't know, sitting a mile away, the wind's going to have to blow it to us, essentially. Okay, so the Fukushima meltdown in Japan, y'all were probably little kids when that happened. There was earthquake. Y'all remember any of that? Y'all were young. Okay. Y'all suck. Because that was like yesterday, you know. It was just a minute ago. Okay, so there was a big earthquake and a tsunami that just destroyed a portion of Japan and destroyed nuclear reactors. And, you know, there was concern that some of that radiation was going to wash across the sea, essentially, and make it to the west coast of the United States. Okay. So, but it had to have some sort of mechanism to get here, you know, be it wind, water, something. And the amount that got over here was very minimal. Amy's going to show you a movie next semester, probably, about Chernobyl. I know y'all are too young to know, to remember anyway. Chernobyl, a lot of y'all probably weren't born, or maybe none of you were. But that was a meltdown in Ukraine, and that place is still radioactive. You have to have special permission to get close to it. Both of these things are searchable online. If you want to see just some scary stuff that Mother Nature does, then look up the tsunami, the Japanese tsunami following the earthquake. It's scary. It really is. If ever, okay, this is a public service announcement. This has nothing to do with any of this, but if ever you are anywhere close to a beach and the water disappears, like the beach extends by a mile, where's that water going? It's going out to sea. And it's piling up, so to speak. It's coming back, you know. People were walking way out, way out. Oh, it's cool. The beach just grew by a mile. And they got killed. Okay, so if you're ever anywhere close to a beach and the water goes that way, your response is to go that way, high ground. Okay, a lot of people died. Indonesia had some, earthquakes that wound up killing a lot of people as well. So anyway, alpha particles, big, slow moving, and they do a lot of damage. So if they touch you, this is truly radioactivity that people are most associated with, or people most associate with radiation exposure. The flip side to it is that alpha particles are not penetrating. Okay, so one hits your body and it's going to expose and it's going to be bad for you, but it's not going to penetrate. So you can, that's kind of weird. As bad as these things are, you can stop it with a piece of paper. Okay, so alpha particles, slow moving, don't penetrate. Beta decay, you can get some penetration with beta emission. So both will undergo, both types of uranium will undergo both of these, and what will eventually happen is that uranium-238 eventually becomes lead-206. Okay, and uranium-235 becomes lead-207. So it becomes a totally different and eventually non-radioactive substance. It takes a long time though. One of the two, the half-life, which we're going to talk about in a minute, is 4.7 years, I think, or 4.7 billion years, I think, or 4.5. The other one is like 700,000 years. Okay, so it's a very, very long time. And what half-life is the amount of time it takes for a quantity of radioactivity to decay to half of its original value. Okay, what I mean by that is this. Let's say we've got, it's just arbitrary numbers, just make it easy. Okay, let's say we've got something that's radioactive, and this circle represents how much radioactivity it puts off. And we're, again, going to assign it a simple number to keep up with, and we're going to say you've got 100, you pick the units of radioactivity coming off of this thing, okay? So half-life is the amount of time it takes that to reduce to half of its original value. What's its original value? 100. Right, so what's half of 100? 50, right. So that would be one half-life. Okay, so if you're given a problem to calculate half-life, and it's on the test, you're going to be given, how much radiation you have. You're going to be given the amount of time it takes, if it's pertinent, the amount of time it takes, or the question is going to ask you after so many half-lives, how much do you have? Okay, so original value was 100. One half-life gave me how much? 50, right. So now your original value is 50. Okay, you're going to have tendencies to think, okay, my original value is still 100. No. Now this is the amount of radiation you have. So this is your original value. So your next half-life, second half-life, would divide that again in half. So now you've got how much?
25.
25, right. So then we could do that again, and your half-life would be 12.5, right? So that would be 3 half-lives to get to 12.5 units of radiation, whatever you want to assign that to. Okay? So, and you could take that down even, again, 4 half-lives would be 6.25. Now we're starting to get to a point where, it's going to be hard to divide it, but 6.25. So 1 half-life gave us 50, 2 half-lives gave us 25, 3 gave us 12.5, and 4 gave us 6.25. It's really simple to calculate, on the test, just draw it out. Just draw it out, and divide it out. It's not that hard to calculate. Okay, so a couple of things on radioactive half-life is that you're going to cover this in radiobiology next semester, so it's kind of a primer for it. Okay, you're gonna cover alpha emission, beta emission, probably going to cover positron emission. Positron emission is what we use in nuclear medicine in some applications. With positron emission, this is where I was going to, say I was going to throw a monkey wrench into the whole, positive and neutral, fixed sizes of the positive charges and the neutral charge. There's a thing called a positron where you can eject a positive charge from the nucleus of the atom that is the same size and charge as an electron, meaning that it's not really exactly a proton, it's positron, okay? And if you want more than that, I'm going to say look it up. I'm not going to confuse you more than that. We're sticking with this right here for the test, okay? But Bushong mentioned positron, so I wanted to touch on it real briefly just to explain that we use positron emitters in nuclear medicine. PET-CT, PET scans, that's what it uses, positron emission. Okay? So there's those things. There's something else I wanted to mention on that. I don't think so. Okay. So in the book, you might have noticed, I hope you did. If you read the book, you should have. Carbon-14. So radioactive half-life is going to be very specific to the type of radioactive material that you're dealing with. Carbon-14 is very common, and we use a lot, actually, in radiometric dating. So carbon-14, if they want to see how long ago something died, and it's been a long time, then they'll, dig up the bone, and it's got to be a bone. It can't be fossil. Fossils, fundamentally, the fossil has no real organic matter in it. It's just, essentially mud has replaced everything. And with fossils, they have to go with the strata in which they find the fossil. But carbon-14, if something died maybe 20,000 years ago, we know within a range how much carbon-14 that thing should have had in it whenever it died. So we can very closely determine within a very small range of how long ago it was that it died. So you've got carbon-14 inside you right now. If you remember back to when we were talking about sources of radiation, there were internally deposited radioisotopes, right? Carbon-14 is one of those. So, you're minimally radioactive. You die and you stop, replenishing carbon-14 in your body. And then, somebody dug you up 20,000 years from now. They could determine within a range when you died based on how much carbon-14 you still have in you. Okay, because carbon-14, the half-life on carbon-14, always want to get this wrong, 5,730 years. And they can assess up to, I think it's around 60,000 years, within a pretty good range of when an animal died. We're being serenaded by something. So things like woolly mammoth, it died off 10,000 years ago. we can assess that. So that's carbon-14 in its half-life. What's that?
We're too ADHD for that.
Can't focus?
Yeah.
Tell them, turn it down if it's, is it, I mean, is it,
Why are
is
they
it too bad?
listening to it so loud?
I don't know. I don't know. I don't know. Let me see who's. Being, the speakers being on a wall like that, sometimes the vibration makes it seem like it's louder next door than what it really is.
Going over the way. I'm serious. It's just white.
Better?
Yes.
All right.
That's right next door.
Yeah.
Did they have it really loud?
It didn't sound like it out there, but, okay, so, again, has no point here, but we used to be over in Pirtle, and there was a practice field outside of our classroom. That's where the Apache Bells went to practice. And, so they were, and sometimes a band, and seminar is the last class that you'll take. It's nothing but tests. Nothing but tests. So you'll have a test over this class, you'll have a test over radiobiology, you'll have a test over patient care, 2 over imaging, 2 over positioning, and a final exam. And we'd have to go out there and say, y'all got to stop, because here's Apache Bell. None of the guys in the class were paying any attention because here's Apache Bells up. I mean, and then there was, just the distraction of the noise. So we'd have to, we finally got them to stop doing that, but it took a while. All right, so what does radioactive half-life have to do with this class? And the answer is not much, but there is a correlation. Okay, so I went through radioactive half-life first because it's easier to diagram and demonstrate. Okay, so review. Why was X-ray dangerous in the early years of X-ray creation?
Because there was no protection against the radiation.
There was no protection against radiation. It went everywhere, right? So there was no protective housing to block anything. Isotropic emissions, if I was shooting an X-ray beam at the back of the room, I'm still getting hit, right? So there's no protective housing. Also, what did Rollins introduce? Collimation and?
Filtration.
Filtration, right. So what does filtration do?
Absorbs scatters.
Gets rid of low energy X-ray beam, X-ray photons. So what we refer to in the X-ray beam being filtered is the hardening of the X-ray beam, okay? So let's say we've got 2 X-ray tubes. Well, let's review a little bit more. What's the main thing that kills the X-ray tube? Heat. What were some of the things that I talked about causing, what does the heat cause?
What does heat cause?
Yeah. Okay, that's how we get rid of it.
Tanning.
Tanning. Okay, what is tanning? Yeah, it's the filament, but maybe a little bit of the anode melting and it's coating the inside of the X-ray tube, right? It's tanning of the X-ray tube. So you got glass, which is very radiolucent, meaning it doesn't absorb a whole lot of X-rays. And then you coat it with metal. And anybody forgot to remove a necklace or lower the pants for a KUB? Yeah, what do you see? Zippers stand out like a light bulb just went off, right? So metal absorbs more X-rays than glass, right? So the more tanning you have, the more you're going to lose some of those low energy X-ray photons. You're going to get more filtration. You're going to get a harder X-ray beam, okay? So that's the preface. Let's say we've got 2 rooms. One room is 5 years old. what did you create in that beam, in that x-ray room, in that x-ray tube over 5 years? Mainly heat, which caused tanning, which increased filtration, right? So every year, and added filtration, yeah, and made it harder. So every year, a physicist is going to come in and they're going to measure the output of the x-ray tube. They don't really care what the average energy of the x-ray tube is. What they're looking for is how many x-ray photons are put out. Does that match what's set on your control panel and what is the peak energy? Okay, so they're going to measure KVP and output, and that's not it, but those are two of the main things as far as technique goes. So this one is brand new. So when they come in and they look at that 5-year-old tube, it's got tanning, which means that the output of the x-ray tube is going to decrease with the increased tanning. Okay, because you've added filtration. So what they're going to have to do is they're going to have to get in there and they're going to have to tweak it so that it comes back up to the output that we want. We want 5 mass to be 5 mass. Okay, you understand? Okay, so with brand new, let's say we set a technique and the KVP doesn't matter, so we're just going to say 75 KVP, doesn't matter in this illustration. And let's say we set a technique of 100 mass, okay? So we set the exact same technique on both sides, KVP in both rooms, 100 mass. All right, so now we want to measure the quality of the x-ray beam, okay? So what we're going to do is we're going to take layers of aluminum, and we're going to put one here, and we're going to put one here, and they're exactly the same, and let's say they're 1 millimeter of aluminum, or some sort of material that would absorb x-rays equivalent to aluminum, okay? So we've got 1 millimeter of aluminum. Let's say that cut this x-ray beam, and you know the mass really, whenever they're doing the test, they're actually measuring the MR per mass, and milliroentgens per mass, or millisievert per mass. So you make an exposure, and it cuts this from 100 to 75. Equivalent. Okay? So it cuts it down to 75. So this test is what we refer to as half value layer. Okay, so it's the amount of an absorber that would be required to cut the intensity in mass to half of its original value. Do I have a half value layer here? Yeah, it's only cut it by 25%. So 1 millimeter of aluminum is not a half value layer. Okay? So maybe we add 2 millimeters of aluminum, and now it's down to 50 mass. Okay? Is that a half value layer? Mm-hmm. Yeah. So our half value layer of a brand new x-ray tube is 2 millimeters of aluminum. Okay? So let's say we put those same 2 millimeters over here, and I'm down to 75. Am I at a half value layer?
No.
Okay, so put that on a shelf for just a second. What does KVP control?
Quality.
Penetration, quality. Quality is penetration, because if you don't have a beam that penetrates, you have no quality. You know, in the tube, it controls the speed of the electrons, all that kind of stuff, right? But fundamentally, in image creation, it controls the penetration because it controls the quality of the x-ray beam. Higher the penetration, higher the quality, right? So what we measure quality in, what we use to control quality, you use, whenever you set your technique, is KVP. But we had the same KVP here. Which one penetrated more? Over here, we've still got 75% of our x-ray beam, as opposed to this one. That's going to be lower quality, lower penetration. So is KVP the definitive measure of beam quality. It's a measure, right? Still penetrated, but the better measure is what we refer to as half value layer. Okay? So when you're talking about the true quality of the X-ray beam, yeah, KVP factors into it, certainly. You know, if I cut this down to 50 KVP, then this would be cut down to maybe 10 mass post, you know, the 2 millimeters of aluminum. But at 75 KVP, on this old, seemingly wore out tube that they've had to adjust over the years, what's coming out of it is a harder X-ray beam that penetrates more, and therefore the X-ray beam is better out of this tube than that one. So why do we use brand new tubes? Why don't we just use all old X-ray tubes? Because they're half dead already, right? It's giving us a better beam, certainly, but it's got 1 foot in the grave, right? So, you know, the older your X-ray tube gets, the better the X-ray beam that comes out of it. All right? Now, does that necessarily mean that's better for the patient? Because, you know, what we could use over here, you know, if we were shooting a patient, is we could use a lower mass value. Okay, we get more penetration, so we could use a lower mass value. So it's better for the patient, right? But is it necessarily better for imaging? And the answer is no, for reasons we'll get to next semester. As you increase filtration and you adjust your technique for it, then what you get is an increase in scatter radiation. Scatter is bad. So this is not necessarily good for image creation, but it's better for the patient. Okay, so higher the half value layer, the more penetration you have per amount created, and the harder the X-ray beam, the higher the quality of the X-ray beam. Okay, so don't conflate the two. KVP is what you use to control quality. The better measure, the best measure of beam quality is half value layer. And the higher the number, the higher the half value layer. Okay, so you know, it may take 3 millimeters of aluminum to get to 50 over here. Okay. See why I started with radioactive half-life? A little bit easier to kind of explain. So any questions on that?
Where does the tanning come in? Like, you know, it makes a layer that's not filtering it? Or?
Yeah, it is filtering it. So the tanning comes in, this tube shot like that 5 years ago. But at year 1, you had some degree of tanning. So what they had to do is they had to go in and they had to adjust the technique because it wasn't putting out 100 mass anymore. It was maybe putting out 90 mass. So they had to adjust it so it still put out 100 mass. And then year 2, they had to do it again because it was, again, putting out 90.
Adjusting the mass?
Yeah. They're adjusting the mass so you still see the same mass, but what's created at the anode is more to compensate for what's coming out, right?
Okay.
So what they're trying to maintain is what's actually coming out, not necessarily what's being created.
So like you read 100 mass even though it could be 150, but
Right.
they're actually still getting 100 mass. You're just,
Right.
that's just what you have to calculate.
Right. What's actually coming out of the tube is the 100 mass value. Yep. Okay. Everybody okay with that? Ish. So that is, you know, is actually both of them are on the test, but you know, that's the more applicable thing for diagnostic imaging. One thing, I'll go back to radioactive half-life, and I'd mentioned this last week, and I mentioned it a little bit today, is that naturally occurring radioisotopes have ridiculously long half-lives. Hundreds of thousands of years, billions, millions and billions of years. All right, so we're talking about nuclear medicine. What they use in nuclear medicine are man-made radioisotopes. And so those are highly, highly unstable, meaning that they undergo all different types of emission, maybe not so much alpha because that's high dose to the patient, even though they're, you know, do some research and you can see that they're kind of playing around with alpha emitters, but mostly what they're going with is, you know, beta emitters and positron emitters. But they're highly unstable, which means that their half-life is extremely short. By extremely short, I mean like, I looked it up and I didn't include it. One of the iodines that we use in thyroid medicine, I think, is 13.5 hours for the half-life.
Is it really potent?
Well, the quantity that they inject into the patient is going to determine its potency.
Okay.
So they inject a very low dose, and how nuclear medicine works is that they tag the radiation to something that an organ system likes. So the thyroid likes iodine, right? So they use the iodine in thyroid imaging, and what we know is about how much iodine should collect in the thyroid once they're injected. So if it comes out, you know, we make an image and we measure how much radiation is coming off of that. And if it's putting out too much radiation, then we have a pathology that's causing hyperthyroidism. Okay, and if it's coming out too cold, that's what we refer to as a hot spot. If we get a cold spot, we know that the thyroid's not absorbing enough. Okay, so that's how nuclear medicine works in a nutshell. It's our modality that really shows physiology. We show primarily anatomy, some exam types of physiology, but nuclear medicine is all about physiology. So we use man-made radioisotopes in nuclear medicine. So, you know, if you know somebody who's going for a PET scan or whatever, just know that they're not going to be radioactive for the next 4 billion years. Okay. Grandma's going to be okay in just a couple of days. All right, so some things here. All right, so you know, then it gets into electromagnetic radiation, and we've kind of talked about electromagnetic radiation. Electromagnetic radiation is anything that demonstrates both electric and magnetic properties. So if you flip over to page 58, you'll see the electromagnetic spectrum. And what you have in that are different types of electromagnetic energy. So you look at the bottom, you've got radio frequency, then you've got microwave, you got infrared, visible light, ultraviolet light, X-rays and gamma rays all the way to the top. So a few things, a few statements, I want to make sure that I get these right and I don't, you know, screw them up. So electromagnetic radiation, anything that demonstrates electric and magnetic properties, most of those behave a lot like light, right? Travel in a straight line, speed of light, all that kind of stuff. Some of them penetrate more than what light does. Light, you have to have something translucent to go through it. Some, you don't have to have anything that's, you know, or really transparent for the light to go through it, really unobstructed. So ionizing radiation in the electromagnetic spectrum is, we're going to recognize definitely X-rays and gamma rays. I would also include that ultraviolet would be at least minimally ionizing. The reason I say that is because if you were to see a radiation burn, a brand new fresh radiation burn, it looks exactly like a sunburn. No difference. A week later, they're going to look totally different. You know, with a sunburn, you might peel, right? It might get flaky and it might peel a little bit. But with a radiation burn, you're actually going to get some decay of some damage to the tissue, deeper damage to the tissue. All right, so in that, you need to understand that not all electromagnetic radiation is ionizing, right? So we're going to recognize, and it'll be on a test, we're going to recognize X-rays and gamma rays. And really fundamentally, the only difference between X-rays and gamma rays is where they originate. We get X-rays by passing electrons close to the nucleus of the atom or ejecting electrons. So that's outside of the nucleus, right? So we create X-rays in the shell around the nucleus. They don't come from the nucleus. Gamma rays come from the nucleus. So fundamentally, the chief difference between the two is where they're created. X-rays outside of the nucleus, just to simplify, X-rays outside of the nucleus and gamma rays inside of the nucleus, okay? So not all types of electromagnetic radiation are ionizing. Right? Radio frequency is not ionizing. X-rays and gamma rays are ionizing, right? So not all types of radiation is electromagnetic, right? Because what are alpha and beta particles? They're radiation, but are they electromagnetic? No, they're particles. So they're what we refer to as particulate radiation. It's still radiation, but it's not electromagnetic. Okay, it's still radioactive. It can still do you damage, but it's not electromagnetic. Okay, so all radioactive, and not all isotopes are radioactive, but radioactive isotopes are just that, they're radioactive, and they are ionizing. So if you have particulate radiation, it does ionize, but it's not electromagnetic. Okay? And certainly then, not all radiation is particulate radiation. X-rays and gamma rays aren't particles, sort of. I'll talk about that in the next section. Okay? Yeah.
Okay, so not all isotopes are radioactive, but radioactive isotopes are ionizing,
Yes.
correct?
Yes.
Okay.
Yep. Any other questions? I don't see anybody else grabbing their heads, so yeah, what you got?
What's the difference between a radioisotope and a radionuclide?
Same thing. Yeah, same thing. Yeah, yeah. Thank you. I meant to, make sure I covered all the terminology, but yeah, it's the same thing. Yep.
Is alpha and beta emission the same as alpha and beta decay?
Yes. Yep.
Just different word.
Just different word. Yep. Anything else?
Do gamma rays really pertain to us ever?
No, nothing. No. I'll just stop it there. No. Anything else? All right, that's all I got then.